Chris, thanks for coming on. Really appreciate you taking the time to have a conversation with me. Would you mind telling us a little bit about yourself before we get started?
Sure. I'm a professor of astronomy at the University of Arizona. I hail from Britain, actually, but left a long time ago for the clear skies of southern Arizona. I work on observational cosmology and a bit of astrobiology, and pretty strong interest in education generally, science literacy, etc. So, the usual university professor, mixture of teaching and research.
Cool. So the topic today was the life and times of black holes. Could you tell me a little bit more about your research on that topic?
Sure. I started actually back as a grad student a long time ago in Edinburgh, working on active galaxies, which are, or quasars, as some people may know that term. And these are galaxies where there's a supermassive black hole in the center that, although black holes intrinsically are black, when they're surrounded by gas and dust and material, they heat it up, accelerate it, it glows brightly, and so quasars are the brightest objects in the universe. So I was sort of studying them and have been in different ways for 40 years.
Cool. And so what has been your main focus of interest relating to black holes? What are the things that you think are most interesting about them?
Well, research in astronomy or many types of research goes in big blocks of time because it takes a while to define a problem and work on it and make progress. If I think people get misled by the froth of headlines about science, that someone goes into the lab and discovers something and publishes it and then moves on to the next thing next week. That's not really how it works. So I've sort of spent big chunks of time answering different questions. The first one I started with was, can you find objects where you're looking down the throat, essentially, of this supermassive black hole? Because the black hole's spinning, and when you look down the poles of the black hole, you have a more unobstructed view to it from a long way away, from billions of light years away. So the first project I did was trying to learn as much about the black hole as close as you could get to the black hole with optical and radio and X-ray observations.
And what did you learn?
Well, what you learn is that these are extraordinary situations of physics, astrophysics. The particle acceleration that's going on, it just blows out of the water, CERN or any big human created accelerator. Overall, the brightness of these objects, these quasars, the brightest of them, these are about 1,000 times the brightness of an entire galaxy, which is 100 billion stars, concentrated in a region the size of the solar system. So just a phenomenal energy density. And so one of the things you learn is that these are gravitational engines, essentially. The engine, the source of all this power, of course, is gravity, the gravity that created the black hole, the gravity that pulls matter onto it and heats it up. And these gravitational engines are extraordinary because their efficiency of converting mass into pure energy is 40%, compared to a star, where with fusion, the energy of converting mass and the efficiency of converting mass into energy is less than 1%. So they're incredible engines of gravity blowing away anything else we've seen in the universe.
So when you say converting mass to pure energy, what is the pure energy form that they convert it into?
It's electromagnetic energy across the spectrum. These quasars have been picked up at every wavelength, from super high energy gamma rays and even cosmic rays down to meter length radio waves. That's about 18 orders of magnitude, 18 powers of 10 of wavelength or frequency. So incredible. And they emit at all wavelengths in between. We can't see all those wavelengths because we may not have satellites sensitive to them, and a lot of that doesn't get down to the Earth's surface. So this particle acceleration zone is putting out energy in this amazing range of wavelengths. And actually recently, just in the news about a month ago, one of these active galaxies, a fairly nearby one, was found to emit neutrinos as well. So it's just very exotic. Neutrino astronomy is in its infancy, and so this is the first active galaxy to be detected in neutrinos.
Why do you think that is? Why do you think this is the first to detect neutrinos? Because we do detect neutrinos from like the sun, right? Quite oftenly.
Right. So neutrino astronomy is hard because, as we know, neutrinos, they're not massless. We haven't yet measured their mass because they oscillate between the flavors, and that's a hard experiment. But they have a very low mass, and they have an extremely weak interaction with anything. They only interact by the weak force, the weak of the four fundamental forces. It's the weak force, and the way it sounds, they don't interact really with light or radiation at all. So detecting them is really hard. Essentially, you go deep underground or under the ice pack or in the ocean, actually, and you look for collisions of the neutrinos with atoms or nuclei, and you measure the sort of collision energy, because they're not going to emit light or radiation. So it's really hard to detect them. And the corollary of that is you need huge detectors to detect them, because they interact so little. That the thing that physics students always learn is a neutrino can pass through 3,000 miles of iron and have a 50% chance of being stopped. That's pretty impressive penetration power. So the penetration power being so great means detecting them is hard, because the sensitivity is low. So you need a huge detector even to detect a nearby one. And yes, we've had neutrino detection from the sun for decades, because the sun's only 150 million kilometers away. When you're talking about millions of light years away, then that's a hard job.
Do you think there are lots of new particles or new atoms being created, new elements being created near black holes? Because during supernovas, there's lots of elements that are created that were not originally there. Do you think a lot of new elements are being created near black holes?
And that's an interesting question. And I guess we indirectly think the answer is no, because we do spectroscopy of these black holes and the radiation zones and hot zones around them. And we can see what these accretion disks and acceleration zones and jets and all these phenomena are made of. And they're mostly made of cosmic material, just we see everywhere, hydrogen and helium for the most part, and then small amounts of carbon, nitrogen, oxygen elsewhere. So we've detected some heavier elements. You can detect iron in the hot gas around a quasar and other things, but we've never found any new elements there. And that may not actually be surprising. A supernova is a pretty extraordinary way to create heavy elements. And it in its small way, it goes beyond the active galaxies and black holes, because a supernova is a blast wave. It's putting out the energy of an entire galaxy in this tiny fraction of time. A fraction of a second actually is the heat reaching billions of Kelvin. And that is a way to make heavy elements incredibly efficiently. So black holes don't actually have that trick.
Gotcha. So what is the typical life cycle of a black hole?
Well, that's interesting, because it took a while to figure that out. The problem astronomers always have is that they die. Astronomers don't live very long. And when your scientists live 100 years, and we've only been doing astronomy for a few hundred years and radio and X-ray astronomy for half a century, it's really hard to see things that take a long time in the universe. So when anything in the universe, like the life story of a star, that was figured out 100 years ago, but that was hard too, because stars don't evolve as you watch them, really. And the same with active galaxies and quasars. So the puzzle was that, well, first of all, black holes are supposed to be black. So why do you have these incredibly bright objects? And then the flip side question becomes, well, why aren't they all very bright? Because what was found through observations with Hubble Space Telescope, really going back to its launch, is that every galaxy has a black hole. That's now a pretty firm statement. And the black hole size scales with the galaxy size in a way that's sort of intuitively obvious. But most of them are dark. They are indeed black holes, and they're big gravitational masses at the center of a galaxy, but they're not bright. They're not like quasars. So quasars are rare. Black holes are common in galaxies, and the question then is why? And the inference, just to summarize a lot of research briefly, the clever inference is that all the black holes in the universe in the center of galaxies spend about 95 to 99% of their time dark or quiet or in between meals, if you like. And then they do binge eating and get incredibly bright, and that's what we see as a quasar.
So how did we discover the first black holes? Because they were theoretical back in Einstein's time early on. What led us to the discovery that they actually exist?
Right, it's an interesting story, and I tried to tell that a bit in my book on black holes. General relativity does lead to the prediction of black holes, because it's an understanding of gravity that, applied to the death of a massive star, implies that the core will collapse to a state which we describe as a black hole where only light can escape. So a density so high that there's an event horizon, a region from which nothing can escape, and that's a clearer prediction of the theory once you work it through. Einstein didn't actually believe black holes existed, even though it's their prediction is a product of his theory. He didn't work on that part of his theory, and he just thought it was a mathematical artifact. And I think what bugged him, and a lot of other physicists too, is that the theory also predicts a singularity, that in the center of the black hole, behind the event horizon, which you can't see inside, there's a prediction that there's a cusp of gravity, so infinite mass density. And that makes no sense. In physics, infinite anything doesn't really make sense. And Einstein knew that, and he just thought, no, they probably don't exist. That's some mathematical artifact of my theory. Well, and he was wrong. He was wrong about a few things and right about most of the things. But so that sort of squashed a little bit the investigation of black holes because he was so influential. And there were other famous physicists who also thought in the 30s, 20s, 30s, 40s, after general relativity came out, who was also skeptical that they were real. And it wasn't really until the 40s, around the war and just after, when physicists like Hans Bethe and others really worked through the theory of what happens when a massive star dies, and they convinced themselves and their colleagues, you should have a black hole when this happens. When a star like 10 times the mass of the sun dies, not the sun won't do this, you get a black hole. And so by the late 40s, the prediction was out there, and then people were confident, yes, should be there. But it took another 2 decades, till 1968, 1969, till Cygnus X1 was the first black hole to be observationally confirmed. So it was a long time. It was over half a century after general relativity was published before you had even the first black hole detected.
And how did we detect it? We detected by like watching stars orbit around something that we couldn't see.
Right. It's right, because the black hole, a solitary isolated black hole, is indeed black, dark, invisible, would not betray its existence. There is a subtle method now. We know how to detect isolated black holes called lensing, gravitational lensing. But that apart, a solitary black hole, incredibly hard to find. However, we've already always known that most stars are in binary or multiple systems. The sun is slightly unusual, in fact, being a single star. So since you have a lot of binary stars, you're clearly going to have situations where one of the stars is massive and dies and leaves behind a black hole, and the other one is still living its life, shining brightly. And in those binary systems, you have the chance of inferring the black hole from the visible companion, measuring its orbit, and Kepler's law gives you the mass of both of them. And if it's more than 3.5 times the mass of the sun, the companion needs to be a black hole. And that was the logic that was used for Cygnus X1 and for the first, really for all the stellar mass black holes that we found so far, which is only about 50 or 60 convincing cases, not that many. And then the reason it was an X-ray source, Cygnus X1 is the brightest X-ray source in the constellation Cygnus, measured in the early 60s with the first X-ray satellites, is this business where when a black hole has a companion, it's sucking material from the normal star onto itself. That material's being heated up and glowing brightly in X-rays and ultraviolet, and so it becomes incredibly bright X-ray source. So it's sort of the same kind of physics that happens in a quasar on a much bigger scale.
Gotcha. We have a question from the audience. Super Squid Hunt asks, what's the difference between a singularity at the center of a black hole and the singularity that caused the Big Bang?
That's a great question. There is a difference. They're both not comprehensible by physics. So I guess the most important statement about singularities is that singularities represent a breakdown of our physics. So the most correct thing to say is that we don't really understand either of those. With that said, I can comment that they are different in the sense that the singularity at the center of a black hole is a prediction from general relativity that it's, of course, impossible to confirm because we can't look inside a black hole. It's an anomaly in the theory, though. Stephen Hawking famously said black holes contain the seeds of their own demise, and the seed he was talking about was a singularity, because he knew, even as he developed the black hole theory a lot in his research, that it was incomplete, it was flawed. And the singularity prediction is an indication of a flaw in the theory, that it's not the final theory of black holes or of gravity. And the singularity that caused the Big Bang is in the same category, because the singularity for the entire universe, which is infinite mass and energy density, also doesn't make physical sense. And it's essentially telling us that we don't understand the initial state of the Big Bang. And that was a true statement when the Big Bang was first proposed 50, 60, 70 years ago, and it's still a true statement now.
How long does it take a black hole to form? Like, do we see black holes at the early universe during the Big Bang? When do we start to see the first black holes, and why?
Well, it doesn't take long, but if we distinguish a little between the small black holes that are left behind when a massive star dies, and then these huge black holes at the center of galaxies. So for the first kind, when a massive star dies explosively as a supernova and leaves behind a black hole, that black hole forms really quickly. I mean, we've not really watched it happen. We've seen supernovae, but we can't see inside to the actual moment a black hole forms. That's beyond our observation. But simulations, supercomputer simulations tell us it happens incredibly quickly. So stellar mass black holes, where that gravitational collapse is a gravitational free fall, they form a black hole in essentially seconds. The black holes that form in galaxies and earlier in the universe, the big ones, that's a different issue, and that's harder to discern because they don't happen overnight. Black holes and galaxies grow in concert, they grow in parallel. Galaxies, we know, grow over cosmic time by mergers and accretion, essentially, mergers and acquisitions. Small galaxies merge together or gather gas and become bigger, and their black holes inside gather gas and material and get bigger, and this has been happening for billions of years. James Webb Space Telescope was partly designed to answer this question of when did this start happening and what were the first black holes like, or did the first black holes precede the first galaxies? Chicken and the egg. We don't actually know the answer to that either. So that's one of the exciting things we anticipate from the James Webb Space Telescope.
Are there different types of black holes?
Not really. One of the interesting things to a physicist is black holes are extraordinarily simple objects. I mean, they're complicated things in physics, some physical phenomenon like the aurora or something, the northern lights. That's very complicated physically. There's a lot going on. There's magnetic fields, particle acceleration. Black holes are actually very simple. They're defined just by a handful of properties, whatever their size. They're defined by a mass. Inside the event horizon is usually how you define it, by the size, which is the event horizon size, also called the Schwarzschild radius. They have angular momentum because they were formed from spinning objects and they spin faster as they collapse, so they will have angular momentum. And that's about it. They don't have charge, we don't think. They really don't have any other properties. If Stephen Hawking is right, they have a tiny, tiny temperature, which is the emission of Hawking radiation, maybe a billionth or a few billionths of a Kelvin. That's not been confirmed. But basically, they're simple physical objects. And it's kind of extraordinary that the very same physics describes something that forms when a massive star dies, which is a black hole, say 3-4 times the mass of the sun, to the biggest black holes in the center of the most massive galaxies, which are a billion times more massive. The same physics applies all the way across 9 orders of magnitude of mass. That's kind of cool.
Have we seen any black holes colliding together?
Yes, that's what LIGO has done for us. So we always knew or speculated that in the vein of binary star systems, which is how we detected the first black holes, with lower probability, you're going to get a situation where a black hole orbits another black hole because you had 2 massive stars and they both died and left behind a black hole, and now they're orbiting each other. So why isn't that the end of the story? It's all general relativity again. The reason that's not the end of the story is that when gravitational situations are changing and 2 dense objects orbiting each other is gravity changing, and general relativity says you emit gravitational waves or gravitational radiation, and that means you're radiating energy away from the binary system. And since total energy is conserved, if you're radiating away energy, the 2 objects are going to get closer to each other, and eventually they will spiral together and merge. So that was known, or as a prediction, for decades, and it was part of the motivation to build the Laser Interferometric Gravitational Observatory, LIGO, which achieved its first detection in 2016 and has now seen over 50 black hole mergers. That was, LIGO will do a lot of things, but that was what it was initially designed for, because that was presumed to be the easiest thing to detect. So yes, we started seeing black hole mergers in terms of their gravitational waves in 2016. We've seen dozens of them since, and this is a whole big and exciting new field of science.
Dima Music asks, are micro black holes real?
We don't know. So theory, again, you can have black holes of any size. General relativity doesn't put a limit or exclude any. So you can have the stellar mass black holes, you can have those huge ones in the center of galaxies, and in principle, you can have tiny black holes. If some evil genius alien empire squashed the Earth overnight to the size of a peanut, killing us all, or a golf ball, that would formally meet the definition of a black hole. And you can imagine any mass suitably compressed will form a black hole, and that could go down to very small scales. In the early universe, when the densities were incredibly high, I mean the very early universe, first tiny fractions of a second, theory does predict that there should have been microscopic black holes formed, small, very small scale ones, much like less massive than a grain of sand, or about that massive, or up to the mass of a golf ball or a softball, something like that. So nature could have made tiny black holes early in the history of the universe. If Hawking is correct and black holes radiate, the smaller ones radiate quicker and they fizz away quickly. And that theory, if we believe it, predicts that essentially all of those microscopic black holes would have long ago evaporated. And so in the present old universe, we shouldn't see any of them. But observational astronomers and physicists like to measure the information and get data and not trust the theory that's not fully confirmed anyway. And so we've been looking, there have been experiments to look for what are called primordial black holes, this category of small black holes early in the universe. And they haven't been found yet. And the exclusions are getting quite tight. It's almost at the level where they probably don't exist.
Gotcha. A similar question. Slicey Slicer asks, have you heard of any scientists creating black holes in a lab? And if so, how does that work?
No, but if you're probably all aware, those of you watching, that there was a scare at CERN probably 7 years ago, where when the Large Hadron Collider went up to a new energy range, it went around the sort of social media and the sort of internet that maybe CERN could make a black hole, and that would be the death of us all. Because if CERN made a black hole with the energy of its collisions, a black hole would fall to the center of the universe and eat up the Earth from the inside, and that would be it. It was sounded fanciful and ridiculous even at the time, and physicists just rolled their eyes and said, "Oh, well, the stuff that's on the internet." However, and they didn't just roll their eyes. The physicists also made calculations, and they'd done this when CERN was built, and they showed that the ability of CERN to make a tiny black hole, because that's all it could ever make, even in principle. The Large Hadron Collider is orders of magnitude, factors of thousands or hundreds of thousands away from creating the density, even instantly, to create a black hole. They'd already done that calculation before this scare, but when the scare happened, the administrators of CERN and some of the leaders of European governments sort of went to CERN and said, "Look, we got to deal with this. We got to nip this in the bud. It's going like wildfire. So please do the calculation very carefully. Put it all out in public." And so the physicists rolled up their sleeves, did a really good analysis. There's a white paper. I don't know exactly where it is on the internet, but it's a 100-page report. So yeah, it's been pretty ruled out that we cannot make a black hole in any lab on Earth, and we're not even close to it, really.
What is the maximum speed that black holes can travel through the universe?
Well, it's similar to the maximum speed anything can travel through the universe. If we're talking about, and I'm assuming we're not just talking about the expansion of the universe, because black holes at the center of galaxies are just moving at the same speed their galaxies are, all moving away from each other due to the expanding universe starting in the Big Bang. If we're talking about black hole movement itself, the movement of a black hole, I would say the most extreme example is a phenomenon called gravitational slingshot. And that's a mechanism that NASA has used to use the gravity of a large object to accelerate a small object to a larger speed, get a spacecraft out into the solar system by swinging it around an inner planet. That's a routine thing in NASA's world. Well, that thing happens naturally with stars. And so it is possible with this gravitational slingshot mechanism that you could have, say, a black hole in a binary system near the center of our galaxy that passes near a very massive object, and so is really accelerated a lot and is ejected, say, from its binary system. So now it's a solo black hole flung at a super high speed out of the galaxy, fast enough to, of course, to escape the galaxy. And I think the highest speed this mechanism can generate is 10 or 20% of the speed of light. It's really fast. So there's a theoretical possibility that single and isolated, black holes have been flung from the galaxy over time. This is happening all the time, but at a very low rate. It would be very hard to prove this, and we haven't proven it yet. But it's certainly a principle. It's a possibility, and also stars, not just black holes. These slingshots will eject stars and planets even. So it may eject a planet from a star system at a very high speed. So you could have there's a thought, have habitable planets, Earth-like planets with life on them that have been ejected from the Milky Way galaxy and are whizzing through intergalactic space. Totally possible.
Is there a maximum speed that if mass was traveling at a high enough speed, it would become a black hole?
Well, it's not. The formation of a black hole is about concentrating mass in a small enough region. And that can happen. It's not so much a question of speed, it's just a question of a process that concentrates matter. It's the gravitational force. And in the formation of a normal black hole, dead star black hole, as I mentioned, that happens in a supernova. And that is a fast process. So that mass that collapses to the black hole after a supernova goes off is falling in towards the center and compressing to the black hole state at a significant fraction of the speed of light, maybe 10, 20% again. The black holes in center of galaxies are formed in a more leisurely way. I mean, they grow over a large period of time, billions of years, day to day, year to year, decade to decade, nothing much happens. Things are moving fast, but not super fast, not at large fractions of the speed of light. So they just sort of grow in a more leisurely way by sucking in whole stars or gas and just growing steadily.
How do black holes affect time? Because black holes with greater gravity slow down time as you get closer. And so why don't we see, as stars are orbiting black holes, that when they get closer, they slow down rather than speed up?
Right. So the theory, general relativity, does predict that time slows down in a gravitational field. It's the very fundamental prediction of the theory. And we've actually confirmed that theory on Earth. I mean, you don't have to go to a black hole or a strong gravity situation. It was a beautiful physics experiment in the 1950s. As soon as we had accurate atomic clocks, they did the experiment. It's been done multiple times since, of course, but it was done over a half century ago. You take two identical atomic clocks and you leave one on the Earth's surface and you fly one in a U-2 or a very high altitude spy plane, and then you compare them after days or weeks or whatever. And the prediction would be that the clock runs slower in stronger gravity, which is the Earth's surface, compared to above the Earth's surface. And that was confirmed. Tiny, tiny fraction of a percent, of course, billionth of a percent or less. So that prediction of general relativity is right. And in the black hole, you just have the extreme version of that, where the event horizon of a black hole formally represents the place where time has slowed down to the point where it stops. It stops cold. So time freezes at the event horizon, which is an extraordinary prediction, and we can't test that. To the question, in the situations of objects orbiting black holes, we're not yet able to test the theory that way. But also these orbits are happening not very close to the event horizon. It's really hard to make observations of stuff really close to the event horizon or stuff orbiting close to the event horizon. So this time, it's called time dilation. This time dilation effect is extremely hard to measure directly close to a black hole.
Winston's mom asks, she's not very familiar with black holes. Are there other colors of holes, like black, white holes, pink holes?
Well, black holes in the center of galaxies, the quasars I started talking about, are, you could call them white holes but they glow in visible light, but they're actually sort of panchromatic holes. They glow in every color almost equally. They glow in X-rays as brightly as they do in optical light, or radio waves as brightly as they do in optical light. So you can't put a color to radiation that we can't see, but they have all, basically black holes grow glow in all colors is the simplest way to put it.
Foxtrot Red asks, does the singularity have an electric field?
Not clear. The basic theory says no, that black holes do not have a net electric charge. However, the theorists are clever, and they've worked on theories where it's possible, since you have plasma, I mean, basically, whatever the material state inside the event horizon is, it's a plasma. It's hot stuff where the positive and electric charges are separated, electrons and protons typically, because it's mostly hydrogen. It is conceivable in a spinning black hole that you generate a dynamo effect, and so you generate a net electric charge and a magnetic field, of course. Again, because it's all inside the event horizon, this is not testable at the moment. But yes, the theory does make a prediction that interior physics could lead to a net electric charge.
Tim West asked that he thought white holes were the opposite of black holes.
White holes are a theoretical concept that have never been observed, and then it's actually very hard to observe them. A white hole is connected to the concept of a wormhole, where you have, a black hole is a sucking thing. It sucks in mass. It's a drain on matter. It does put out energy. So if it's not formally a white hole to call a black hole that's very active and glowing a white hole. I think when people talk about white holes, they're talking about sort of the opposite of a black hole, and that could only happen when there was a connection, an interconnection in space-time, where stuff was going in one side and then coming out the other side. That's what most people understand by white hole. And in the theory of general relativity, such an interconnected space-time with a wormhole and a white hole on one side and a black hole on the other, it's possible in principle. It's theoretically possible. Of course, lots of things are theoretically possible. And some good physicists like Kip Thorne, Nobel Prize winner, have written about them in popular books, which I recommend that one particularly. But it's never been observed, and also nature may not make such a situation. Space-time in our universe is actually kind of dull. It's very boring. It's mostly flat. Black holes, where it's highly curved, are very unusual parts of space-time. Most of the universe is really dishwater, dull, flat space-time. So we don't really think the universe is riddled with interconnected space-time and wormholes and white holes and black holes in pairs. That would be nice. That would be cool, but that's not our universe, apparently.
GWJ asks, how do black holes get destroyed or stop being black holes?
Well, in the theory according to Stephen Hawking, which again has not been confirmed, there's a mechanism called Hawking radiation, whereby a black hole has another property. I said there are only three properties. If Hawking is right, that would be a fourth property, temperature, has a small temperature. And that means the black holes are radiating at a very, very low level. They're not totally dark. And the inference of that, if E equals mc squared, is that they're also evaporating, because losing energy is equivalent to losing mass. And so Hawking's idea, Hawking radiation, carries with it the implication that black holes are slowly evaporating. And because the radiation is very feeble and low temperature, the evaporation rate is extremely feeble and slow. So the prediction of how long it would take a sun mass black hole, not the sun, because it's not going to form a black hole, but a black hole with the mass of the sun, is 10 to the 68 years, 1 with 68 zeros. That's how long it would take the black hole to be destroyed by evaporation, essentially. And the evaporation rate goes up with the mass of the hole going down. And so I mentioned these primordial black holes that possibly could exist in the early universe are very low mass, and they evaporate really quickly. The biggest ones in the center of galaxies have phenomenally long evaporation rates. I think the formal lifetime of the biggest black hole we've ever found in a galaxy, 20 or 30 billion solar masses, is about 10 to the 98 years, 1 with 98 zeros. So that's how long it would take the biggest black hole in the universe that we know so far to go away.
Super Squid Hunk asks, what form does Hawking radiation take? Is it heat or electromagnetic?
You can think of it either way. I mean, it's very, very low wavelength radiation. So it's below, it doesn't even really feel like heat is the right word, because it's not infrared. This is exceptionally long wavelength radio waves, because the effective temperature of Hawking radiation for a normal dead star black hole is a few billionths of a Kelvin, a few billionths of a degree. So it's not really heat. That's not enough heat to call it heat. That's really radio waves.
So in Hawking radiation, it uses virtual particles and particles and antiparticles coming into existence, and then one of the antiparticles going into the black hole to cancel out something like that. Do virtual particles actually exist? Have they been confirmed yet?
Yes, the existence of virtual particle-antiparticle pairs has been confirmed in physics experiments, actually going back decades, maybe 50 years now. So basically, and it comes down to the fact that the vacuum, what we think of as the vacuum, what a physicist would call the vacuum, is not nothing. There's no real thing as pure vacuum, because quantum theory predicts that even a pure vacuum will have a very small, low level of potential quantum energy, a tiny, tiny modicum of quantum energy. The potential in the vacuum, therefore, is to create particle and antiparticle pairs, because it takes energy to make particles, or particles and antiparticle pairs. And so when you go through the math, which is quantum field theory, it's pretty high level physics, you can predict that these particle-antiparticle pairs should come in and out of existence, and they go out of existence quickly, because any antiparticle will almost immediately meet a particle, and then it disappears again, producing that tiny amount of radiation that it started with. So you can predict that effect. And to answer the question, which I can anticipate, of how on earth do you know this is happening? Well, if particle-antiparticle pairs are coming in and out of existence evanescently at a very low level, out of what we thought might have been pure vacuum, that effect should create a tiny pressure. Any net amount of energy creates a pressure, and that pressure was measured in a physics lab. So it was a very subtle physics experiment. So it seems that particle-antiparticle pairs do exist, that they can come in and out of creation of the vacuum. And in the Hawking, to connect it back to the Hawking radiation, this is an effect that leads to the net evaporation and radiation from a black hole. It seems like you're getting something for nothing, but you have to remember that these particle-antiparticle pairs are being created from the vacuum. So you're drawing, it's like you're creating a little deficit. You're drawing on the vacuum for the impetus to create these particle-antiparticle pairs.
Slicey Slicer asks, do black holes leave behind any residue?
We don't know. It's a good question, because we've never seen black holes disappear. We've only ever watched black holes be created in the death of a star. We've watched them merge with LIGO, and we've watched them exist and grow very, very slowly in the center of galaxies. So we've never seen a black hole evaporate and disappear, so we don't know what will be left behind. In the theory, no, they disappear completely, and they leave. The radiation then flees the scene at the speed of light, and there's nothing left.
So that leads to the question of the information paradox. Is information lost if black holes deteriorate to nothingness?
Yes, that's part of the information paradox. The information paradox has its inception. Well, just to start, what do black holes have to do with information anyway? The physics answer would be it's the entropy. Information is low entropy and disorder is high entropy. And black holes have very high entropy. They're highly disordered, because if you think about it, inside the black hole, you can't say anything about what's going on inside the black hole. Whatever organized information went into it is now invisible to you once it's past the event horizon. So just in an intuitive sense, it's clear you're losing information. You could toss encyclopedias into a black hole and they'll never come out. Well, you just lost all that information. So you can think of any number of examples of why information seems to be lost in a black hole. So what's the big deal? Why should we care about information being lost? Is that a problem? It's not a problem for black hole theory, but it's a problem when you connect it to quantum theory. So our two great theories of physics are general relativity for gravity and quantum theory for the small scale. And the situation of a black hole gets to a problem with quantum theory, because in quantum theory, particle interactions should proceed forward and backward in a completely symmetric manner. where you exchange the particles for antiparticles. It works the same way. You run the time backwards and it runs the same way, and you can observe that in the lab. So there's a very high level of symmetry about quantum interactions. But if you now imagine particles interacting and going into a black hole, then that is no longer a reversible process at the quantum scale. And so you violated a premise of general relativity. Have you really violated it? Well, you don't know, because you can't observe what happens inside the event horizon. But on its face, that's a problem with quantum theory. It's a disagreement between what quantum theory says and what black hole implies. And that's never been, and that is the heart of the information paradox to a physicist. And it's not been fully resolved, or even partially. It's been partially resolved because there's a lot of clever people writing papers every year on this, but it's not been fully resolved. So it's an outstanding problem of theoretical physics.
Efont also asked, what do you think the solution is?
Well, firewalls were popular for a while, so there was an idea that the information, so there are several. There's the holographic principle, which says that the information is not completely lost as things fall into a black hole, but that it's essentially imprinted on the event horizon the way a hologram would be, on the surface itself, the black hole surface. Again, it's very hard to test. Another idea gets over the information paradox by just providing a mechanism called a firewall, where outside the black hole is a regime of intense radiation from quantum effects in the vacuum that destroys the information you would otherwise have in a quantum interaction. So, but these are sort of crutches there, if you like. They're testable in some indirect way, and they've not really been fully tested. I don't have a favorite. I don't have skin in the game. I'm not a theoretical physicist, and I don't have a favorite among them. And there's a lot of debate. I mean, these are not resolved by any means. There's probably 6 or 7 mechanisms people have put out there to try and account for the information paradox.
Mr. Creanine asks, how do you resolve the holographic principle of the coincident Schwarzschild radius volume capacity, and how much does the holographic principle impact your image of space-time?
So I think that's a technical enough question. It's even beyond my pay grade. I'm not sure I understand it. But the basic answer on the holographic principle is, the holographic principle is only making predictions that are indirectly testable, if at all. And it's not even a fully developed theory, I would have to say. So the people who work on this theory don't consider it complete. They don't consider it to make unique predictions that can be tested. So I'm an experimentalist and observationalist, so I have a slightly skeptical view of theory until it makes testable predictions, and holographic principle is not in that category yet.
Bloviator Bomber asks, what is your thoughts on the multiverse? Well,
that's sort of beyond the black hole arena, but it's the principle that if the universe began, if the Big Bang was essentially a quantum event, which we think is the case, because whether or not the initial state was a singularity, certainly the universe was once smaller than a subatomic particle. So you have to think of the formation of the universe in fundamental terms as a quantum event. And if the universe was a quantum event, then you're led down the road of considering that the precursor state, however we describe that, could have included other quantum events, because there's indeterminacy, uncertainty principle, various other quantum principles applying. And that becomes the basis, essentially, for hypothesizing that the universe was not a unique event, and that there could have been other events, other space-times with different properties created from whatever the substrate state that preceded the Big Bang was, that we don't understand very well. So there's a lot of caveats here. And that's the essence of the multiverse. And to some people, that's a controversial subject. Some physicists and many philosophers consider it metaphysics. It's not testable. And I'm an observer and an experimentalist, so I will always be a skeptic of the multiverse idea, however appealing it is in principle or however sexy it is. And yes, it gets a lot of airplay in the media and the internet until it makes a testable prediction. And so far, it's not.
Good question asked, does E equal mc squared point to a real conversion of energy into matter?
Yes, because it is an equation, and you can go in both directions. Um, so you can have it as a temporary thing or as a sort of more permanent thing. The temporary thing was something we were talking about before, is the drawing on vacuum energy to create particle-antiparticle pairs. That's a sort of temporary, bank balance thing where you draw down your bank balance and create particles and antiparticles, but you have to give them back. You have to pay them back in a very short period of time. But also equals mc squared works on a much longer time scale as a balance sheet that goes in one direction or the other. So in any star, the fusion process is essentially the conversion of a very small amount of rest mass into radiant energy, and that's how stars shine. So stars everywhere in the universe are a perfect example of routine unidirectional E equals mc squared. So you can convert mass into energy, and then you can convert energy into mass because you can have vacuum energy that creates particles. So you can go both ways.
Gotcha. Halsoy asks if black holes are pure energy at the singularity, or if there is actually any raw mass that is the cause of the extreme space-time bending.
In the question asking about the singularity, the simple and correct answer is I don't know, nor does anyone else, because the singularity is not a comprehensible aspect of black holes, because it's not an energy cusp, it's a mass cusp. It's infinite mass density. That's formally what a singularity is, and that's not a physically meaningful concept. So it's easier to think, in general, in terms with black holes, it's easier to think of their mass and their properties of mass and how it's distributed than the energy. Energy is a sort of byproduct, if you like, of the existence of a mass hole, a black hole.
Gotcha. Super Squid Hunk asks, have you seen the movie Interstellar, and how did you feel about they handle the time dilation due to gravity? I feel like they got the slingshot maneuver around the black hole massively wrong.
Right. So I like Interstellar. I mean, maybe my bar is set pretty low because there's a lot of movies that mangle physics really badly, and Interstellar did not generally do a bad job. I mean, if you have a beef with Interstellar, you got to take it up with Kip Thorne, aforementioned Nobel Prize winner out of Caltech, because he was the scientific consultant on Interstellar. So why I give Interstellar high marks is I enjoyed it as a movie, and they really did try pretty hard to represent black hole physics correctly. For example, something that not so many people know, the research team behind it, Kip Thorne's team at Caltech, to generate the animation, the simulations, the CGI of Interstellar, they did supercomputer relativity calculations of that situation, a massive spinning black hole and nearby objects. And they learned how to do those simulations well enough that research generated, I think, 5 or 6 research papers already. And that was purely in the service of that movie. So that's a beautiful example of science and art combining, because they were doing pure gravitational research and it fed right into how the movie looked. That's great. But as you point out, the slingshot maneuver, they go wrong. And I could point out another times not enough to point out a few other blemishes or physics goofs or extensions of reality that they did. And I think it's fine. I think you always have to give an artistic project a pass on some things. We could take The Martian as an example, and it obviously got a lot of things about Mars and space travel right, and it got a few things egregiously wrong. And I think you can give any movie a pass and some artistic license.
Slicey Slicer asks, would it hurt to be sucked into a black hole?
And the answer is that depends. So the physics of falling into a dead star black hole, the kind we would see in the nearby Milky Way, the emphatic answer is yes, it would hurt. Actually, I don't even know if hurt is the right word. We need a new word, because when you fall into a normal mass black hole, what kills you is the stretching force, the tidal force, the difference in the gravity between your feet and your head, or one side of your body and the other, is enough that it will pull you apart like taffy. I mean, but it's not like taffy. It's really, you're being pulled apart on all scales equally. So you're being pulled apart at the level of bones, nerves, tendons, fibers, molecules. And that's such an alien situation of hurt that I think hurt isn't a good enough word for it. So I'm sure it's just a terrible thing. However, there's a good news about black holes. As you go up the mass scale, and we now know there are billions of times the mass of the sun black holes, there becomes a mass of the black hole where the total gravity, of course, is getting higher with the mass, but the stretching force is lower. There's bigger black holes have less tidal force near their surfaces, near their event horizon, or stretching force than the little ones. So about 1,000 times the mass of the sun and higher, and there's plenty of those. If you fell in, you might feel a little squeamish. It might sort of be a little nauseating or whatever. Something's going on with gravity, and you're not feeling completely normal, but you could survive it. It's a survivable event. So in principle, humans or physical objects could survive falling into the big black holes in the universe. And they're not even that extreme. The mean density inside the event horizon of one of the biggest black holes in the centers of galaxies is much less than the density of water, like 100 times less than the density of water. So we think black holes are extreme, but that's not a very extreme density. So yeah, you could even imagine swimming around in there.
Native Atheist says, I hear we're in a black hole. Is that true? Are we in a black hole?
Well, not directly. So people have asked or wondered whether the universe, the expanding universe itself, meets the definition of a black hole, especially since it's a sort of self-contained entity expanding space-time that formed from something we think was close to a singularity. So it's a reasonable question. It's an analogy that would stretch so far as to be broken. So I don't think you can rightly describe the universe as a black hole. So black hole is defined really by its event horizon and a region, within which you cannot see, and the very high density of mass within that. The universe doesn't really have an event horizon. The current big old universe that we're just moving away from all of the galaxies in, it has a horizon that a limit to what we can see based on how far light could travel since the Big Bang, 14 billion years. So that's called a horizon, a cosmic horizon. But it's not really the same as an event horizon. So analogizing the universe in a black hole, I think, is flawed enough that it doesn't actually make sense.
What is information? Is it physical?
Information is the basis of everything we do in the modern world. It's the basis of the TV, the TV and the internet and everything we spend our daily lives on. So the physics and the theory of information was developed in the 1950s by Claude Shannon, who was a brilliant physicist and information scientist before that term even meant anything. So information is connected in a direct physics way to entropy or disorder. So information is presumably order. You can understand that generically, that if we have information, it must be something ordered, because a chaotic substance that's random and has no pattern and nothing in it, there's no information in there, right? It may have a size and a temperature, but there's nothing to say. So I'm doing all this without the physics and the math, but basically information can be described as, in a physics sense, as the number of equivalent microscopic states. So if you have a black hole that has a huge number of equivalent microscopic states, because we don't know what went into it and we can't inspect that, then its information content is very low and its entropy is very high. On the other hand, if you have highly ordered matter, where it's a structure that you can interrogate and see and get a lot of information out of, then you've got low entropy and high information, DNA or something like that. So there's a set of situations in the natural world which involve a spectrum going from high information content down to low information content, and that's also a range of entropy. And what we did with technology in the 1950s was we learned how to codify what a physicist would define as information into digits, binary digits, on and off. So we just turned the physics definition of entropy into a series of ones and zeros, light and dark, on, off electrical current, which is the basis of our modern society.
Winston's mom asks, how old were you when you fell in love with space and science?
Well, I lost the accent because I came here as a child and then again after grad school. I grew up in Britain, which is a cloudy country, rainy mostly. So I never saw a lot of stars growing up. So I didn't get into astronomy young. A lot of astronomers start as kids, see the sky, get a telescope, trade up to bigger and bigger ones, and bang, they're professional astronomers. That wasn't my path. The gateway drug for astronomy is physics. Usually, most people who do astronomy PhDs did physics as an undergraduate, and that was my path too. So I fell in love really with physics first, and as a high school student probably, and then as an undergraduate in London at Imperial College. And physics and astrophysics or astronomy is just the application of physics out into the universe. Just the amazing idea that these laws of physics that we've derived, over a few hundred years since Newton, basically, can somehow describe the center of a star or a galaxy billions of light years away, or the state of the universe 14 billion years ago, and do so in a way that we understand it, can make predictions and test them. So it's the application of physics into the universe, which is extraordinary that it works as well as it does.
Awesome. Super Squid Hunk says, this dude is great. Really fascinating info here. Thank you, Super Squid Hunk. And the last question is, what do you think of the possibility of wormholes or the Einstein Rosen Bridge?
Well, these are theoretical concepts. Einstein and Rosen, just the background of that question, is Einstein and Rosen worked together on a number of physics paradoxes, actually. They were also working on fundamental quantum theory and indeterminacy in quantum theory that they didn't agree with. So these are issues of, the information content of a black hole. They relate to the information paradox and sort of hypothetical situations where you might see that paradox in play, or be able to travel in space-time. That's the wormhole example. So I've probably already said that these are theoretical concepts that are legitimate within general relativity. They arise from the theory, but observation, as far as we know, and so far, has not shown that the universe contains wormholes or Einstein-Rosen bridges. But a big caveat on that is our observations are still pretty primitive. I mean, these are very difficult things to observe, even in principle. So I would say the fact that we haven't seen them yet is not a really strong exclusion on their existence. It's just a fact that it's young days, early days in black hole theory and observation.
Awesome. Well, we have been going for about an hour, and you said you have to go right about now. So I want to be respectful of your time. Do you want to give any links or references where people can find out more about your work?
Sure. I don't have any immediately, but if you just Google Einstein's Monsters and my name, you'll see the book I wrote on black holes, which is a few years old. Still true. Things haven't gone out of date with that book very fast. So that's the book I wrote, and I got excited about black holes writing it, and I'm still excited about black holes. And I enjoyed your questions. Very wide-ranging, sophisticated questions, covered a lot of ground, and I appreciate the interview.
Absolutely. Thanks again. I really appreciate it, and I hope you have a wonderful rest of your day.